Okay, good afternoon, buon pomeriggio. So my name is Alessandro Armando. I'm a program co-chair of the ITASEC conference, and this afternoon I have the honor to act as a moderator of the session devoted to the keynote, our first keynote speaker, who is Lujo Bauer from CMU in the USA. Let me just briefly introduce Lujo to everybody, even though I guess you know already Lujo from his prominent activity in computer security. So Lujo is a professor of electrical and computer engineering and of computer science at Carnegie Mellon University. He received his Bachelor of Science in Computer Science from Yale University in 1997 and his PhD also in Computer Science from Princeton University in 2003. Lujo is a member of Scilab, the Carnegie Mellon Computer Security and Privacy Institute, and serves as the director of Scilab's Cyber Autonomy Research Center. He has contributed on many aspects of computer security and privacy, including the development of high assurance access control systems, the building of systems in which usability and security coexist, and the design of practical tools for identifying software vulnerabilities. His recent work focuses on developing tools and guidance to help users stay safer online, and on examining how advances in machine learning can or might not lead to a more secure future. Lujo served as the program chair of the flagship computer security conferences of the IEEE, including the IEEE Security and Privacy Symposium and the IEEE Euro SMP Symposium, and the Internet Society, and is also associate editor of the ACM Transactions on Privacy and Security. So today, which I'm really gratefully accepted to serve to intervene in our conference as a keynote speaker. Today, Lujo will speak about on the practical risks and benefits of artificial intelligence to cybersecurity. This is, of course, a very interesting and timely topic. So thank you very much, Lujo, and the floor is yours.
Thank you very much, Alessandro, for the introduction. Thank you, and I'm grateful also to all the other organizers for inviting me and giving me the opportunity to speak to this audience. So I'll talk about the practical risks and benefits of AI. Mostly, I'll actually be talking about machine learning. I'll be using the two terms a little bit interchangeably, even though they're not. Before I launch into my talk, I also want to say that a lot of what I'll be covering is based on work that I've done with my wonderful colleagues and students. So I want to mention Mike Reiter, who's now at Duke, Mahmoud Sharif, who started out as a student with me, but is an upcoming professor at Tel Aviv University, my current student, Keen Lucas, and there were a number of others who made key contributions. So the background for this talk is something that we all know, namely that AI and machine learning are becoming more and more influential in society. AI and machine learning are responsible for lots of cute things, maybe like playing games, and maybe things like automated driving, which doesn't really work completely, and unclear how necessary it really is anyway. But AI and machine learning are also used for lots of other more important tasks, such as predicting the weather, or diagnosing illnesses, or even designing special medicines. So very increasingly important, and there's every sign that they will become more important yet. Now, all of these amazing uses of AI, if you are a computer security person, come with a little bit of an asterisk on them. And this asterisk, it has to do with the fact that we know that machine learning algorithms are fragile. So most of you have probably seen this image of a very famous panda. The reason this panda is famous is because it's been shown that if this panda obscures his image just a tiny bit with something that looks like noise, in fact, this noise is multiplied many times in order for you to be able to see it, then the resulting image of the panda combined with noise turns out, in the eyes of a state-of-the-art object recognition algorithm, to be a different animal called a gibbon. So here a panda has successfully disguised himself as a gibbon. And we've known that machine learning algorithms, state-of-the-art machine learning algorithms, have this strange fragility almost as long as we've had machine learning algorithms that outperformed humans. So in about 2015, we started having these classifiers that could reliably do object recognition better than humans could, and at about the same time we realized they also had this weird behavior with respect to these quote-unquote attacks. Now, what I'm going to be discussing today is, what do these attacks mean in practice? You probably don't expect that there are lots of evil pandas running around trying to disguise themselves as gibbons or other animals. But this behavior of machine learning algorithms is concerning, and I want to explore to what extent is it concerning for real uses of machine learning. So ways in which, context in which we actually might be deploying machine learning in reality for practical use. I'll spend probably 85% of my time on this negative side. What are the risks? Can attackers actually defeat machine learning as it's used in the wild? And then I'll talk a little bit about defenses, both where we are and where we would like to be, and also about implications for computer security in general. So let me launch into this first segment. What I've been interested in, what my group, part of my group, has been working on for 5 or 6 years now, is to better understand what this ability for the panda to disguise himself as a gibbon means in practice. And in particular, the way we originally looked at this is to ask the question, can an actual attacker fool a machine learning classifier? Answering this question involves breaking it down a little bit. So the first thing we might ask is, okay, let's first fix an attack scenario. Let's come up with a particular use of machine learning in the wild, of machine learning in practice, where we can imagine that an attacker would gain some advantage by defeating or tricking the machine learning algorithm. So a setting where somebody actually gets a benefit from defeating the machine learning algorithm, and also has some ability to influence the algorithm. Now, if we have such a scenario, then we can look in a little bit more detail at exactly what is the capability that the attacker has to influence the algorithm. In this attack where the panda turns into a gibbon, the attacker has per pixel 100% complete control over the image. Right? It's likely that in practice an attacker might not have that much control, and we break down the constraints into saying how precisely can the attacker manipulate the input, and what can the changed input to the machine learning classifier look like. Now, these look like they might be the same question, but it actually turns out that there's some nuance and they're different, and I'll illustrate by example of what the difference is between these two ways of looking at constraints. So the first scenario that we started looking at in any detail is one that has to do with fooling face recognition. So we can imagine there are already many uses of face recognition in the wild. For example, I used to use face recognition to log onto my phone, right? I'd have to point the phone camera at my face before my phone would unlock. Face recognition is also widely used in surveillance scenarios, right? So there are cameras all over the place, including at places like airports and security checkpoints, and often the authorities run sophisticated image recognition algorithms over this video to try to detect if this video contains particular people who are wanted by law enforcement, for instance. So we have a scenario. We have a clear incentive for an attacker, right? If I'm wanted by law enforcement, then I might want to somehow trick a machine learning algorithm into not realizing that this is me walking through an airport, right? Because I want to remain undetected. Or if somebody is trying to log onto my phone as me, they might want to trick my phone into believing that my phone has seen me, the legitimate owner, instead of whoever it was that's trying to attack it. So now let's look at the constraints in these particular cases. In the panda case, again, there was per pixel, the attacker had per pixel control over the input. In these particular scenarios, you can imagine that the attacker doesn't even know where the face recognition system is or where the computer is. So the attacker definitely doesn't have control over the digital input to the face recognition engine. What the attacker might be able to do is somewhat change their appearance on camera. Maybe they can wear differently colored clothing or a hat, or they can stand on a particular side of the image, or maybe they can wear some makeup or fake nose or something like that. Right? But certainly not per pixel control over the image. And here comes some of the nuance in what the attacker can do. There's an additional constraint, at least for some of these scenarios, for example, when walking through an airport, which is that for an attack to be successful, the humans around, the defenders, can't notice the attack. That is, I can probably defeat face recognition that's running on video from an airport by putting a paper bag over my head and then putting somebody else's a picture on top of this paper bag. Right? And this might fool face recognition, but it's certainly not going to fool any human at the airport. Right? And everybody will notice that this very weird person with a paper bag over their head, and probably they'll point me out to a policeman who'll come and take the bag off. Right? So this is a way in which, even though the attacker is capable of an attack like this that might fool machine learning, this attack is not really an attack in practice, because it won't fool the humans who are also in the picture. All right. So we have the setting where we think we know what the attacker's capabilities are. So now let's see whether in this setting we can mount a successful attack. I'll talk about two different approaches. This is our first attempt at doing this. I'm keeping these constraints around just as a guide for what the attacker needs to do. In this first attempt, what we do is we start with the same attack that allowed the panda to be misrecognized as a gibbon, but then we add a bunch more constraints, and I'll talk about each one of these constraints in turn. And these constraints jointly, hopefully, will satisfy these properties that the attack needs to have, like robustness to camera position, lighting, and that somebody won't notice the attack, and so on. Let's go through these one by one. So the first constraint is one where we say we will run exactly the same attack as before, which will modify an image, but then we'll throw away all of the modified pixels except the ones that are on the surface of the shape of eyeglasses. And the reason we do this is because, remember, what the attacker is trying to do is modify their appearance. So how can the attacker modify their appearance? Well, again, they can wear makeup or different clothing or a hat or something like that. It turns out that face recognition algorithms, typically the first step in their pipeline is to crop out a person's face relatively narrowly and then run face recognition only in that small rectangle. So basically, whatever modifications an attacker tries to make to their appearance, they have to be within the small rectangle of the face, which actually rules out a hat, possibly even rules out earrings, and so on. So we went as eyeglasses as one candidate way of fooling recognition. So here, this is what it might look like. Suppose that Vicky McClure is trying to impersonate Terrence Stamp. These are both actors. We would run the normal attack on the image of Vicky McClure and just throw away all the pixels that are not on the surface of eyeglasses. And this is what this might look like. Now, the next step, the next step we perform is to smooth out the pixel transitions. So this has to do with actually being able to print out these eyeglasses eventually and wear them. If you look at any image that's taken with a camera of physical reality and you look at adjacent pixels, you'll notice that the transitions between pixels are smooth. Right? Even though you might see some high contrast lines when you are zoomed out, when you're zoomed all the way in, adjacent pixels are so softly blend into each other. Right? And this is different from what you would get in a straightforward application on one of these attacks on a classifier. In one of the straightforward attacks, you get jagged transitions that you actually, even if you could print them out, a camera would not capture them. So the camera would sort of destroy a lot of the detail in the attack. So we essentially add a constraint term to the optimization that makes it so that instead of pixel transitions that we might get like here on the left in green, we get smooth pixel transitions like you see on the right. The next thing we do is we notice that These attacks operate in RGB space. Any color that you can express using an RGB triple is fair game. But in practice, that doesn't work so well because you can't actually print out any color. Or if you print it out, you print it out as a slightly different color, and then when you take a picture of it again, that changes what the RGB triple actually is. So we essentially create our own color map by creating and printing out an ideal color palette, taking a picture of it with a camera, and then seeing what's the correspondence between the colors that we try to print out and the colors that we see when we after printing out and taking a picture of this palette. And we use this to define what we call a non-printability score. So basically a penalty for colors that are hard to print out or that can't be printed out. And then what we try to do is when we're creating one of these attacks, we also try to minimize the non-printability score of the colors involved in the attack. The last phase we add is adding robustness to pose. I talked about how the attacker doesn't know exactly where their face will be on camera. Maybe they have to walk past the camera and the camera will capture them from different angles. So how to account for this? And it turns out to be pretty straightforward. A way to account for this is simply to instead of using a single image of an attacker to create an attack, is to use a whole set of images of an attacker and try to find attacks that work for all of the images in the set. So if we're trying to find a pair of eyeglasses that will cause misclassification, then try to find a pair of eyeglasses that works not just for one image, but actually attach them digitally to many images of the attacker in which the attacker is oriented slightly differently, and only work with eyeglasses that work for all of the images or majority of the images. Okay, so how does this work? We need some sort of test environment in which we can examine this. So this test environment, first of all, has to exist of a face recognition engine. So we train a couple of state-of-the-art face recognition engines. In particular, we experimented with ones that are called VGG and OpenFace. We trained them to recognize either 10 or 143 people, and these people included a number of celebrities from a data set that's often used for training image classifiers, as well as a set of us who were participating in this work. And the reason we were training the classifier to also recognize us is because we were going to be the ones mounting the attacks. We would have liked it if some famous celebrities helped out, but we thought that our funding didn't stretch that far. So now that we have a trained classifier, then from among the people who are willing to act as attackers, we at random pick somebody to be an attacker, and then from among all the people that the classifier knows how to recognize, we at random pick a target to impersonate. Right? And given this combination of attacker and target, we cause the algorithm for generating attacks to produce a pair of eyeglasses. So the algorithm produces an image of a pair of eyeglasses. We print these out on a standard photo printer on photo paper. We cut out the shape. We glue the shape to a pair of normal eyeglasses. Then we have the attacker wear the eyeglasses. We take video of the attacker. We extract frames from the video, and then we classify the collected images. And in particular, we measure the fraction of images which are misclassified as the target of the attack, who in this case is Carson Daly. So how well does this work? Often it works pretty well. In this particular case, Mahmoud impersonating Carson Daly, we could create a pair of eyeglasses that when Mahmoud wore them in physical reality, 100% of the time he would get misclassified as Carson Daly. Now, this didn't work for every pair of attacker and target, but it seemed like about 2/3 of the time when we randomly picked an attacker and a target, the attack would work completely, and 1/3 of the time it wouldn't necessarily work so well. Okay, so where are we now? We're trying to figure out, do attacks work in reality? We figured out that we showed that they do work, at least to the extent that yes, it is possible to generate a physical object that somebody can wear, in this case a pair of eyeglasses, such that this will cause them to be misrecognized by a state-of-the-art face recognition engine, at least in some scenarios. I haven't addressed a few things. I talked a little bit about pose, but I didn't give any concrete results about that. We haven't looked at all about the effect of lighting. So maybe the attacker needs to walk through the airport both in the morning and in the evening and buy some windows, and it might be sunny or not. Does this have an effect? I also didn't talk about, does somebody who sees this attacker, do they notice that anything is wrong? You might have noticed that the eyeglasses on the previous slide, they looked a little bit strange, right? So if somebody saw those eyeglasses, maybe they would immediately think, aha, person is wearing funky eyeglasses. It must be an attack. So we try to add to the constraints that I talked about, the constraints that were used in generating an attack, to try to account for these two constraints, these two sets of constraints that I haven't yet talked about. But it turned out that no matter how hard we tried, we couldn't really come up with a mathematical formulation of what it means for eyeglasses to be reasonable looking. We tried a whole bunch of different approaches, but in the end, nothing worked. We couldn't constrain the algorithm to produce more normal looking eyeglasses. So then we completely switched directions and decided to try to create attacks like this using a different method. In particular, the insight that we were trying to utilize is that it might be possible, even in cases when I can't mathematically express the constraint that I want the attack to meet, it might be possible to train a machine learning algorithm to learn this constraint. So now we're this constraint of inconspicuousness, which I can't mathematically define. What I'm going to do instead is I'm going to teach a machine learning algorithm to somehow learn that constraint by example. So how do I do that? Well, what I can do is I can easily go out on the internet and do Google image search and find a whole bunch of images of real eyeglasses. And now I can use this set of images to train a generator network. So a machine learning algorithm that when I give it some random number between 0 and 1, it'll produce a pair of realistic looking eyeglasses for me. And in particular, the way we did this is in a so-called GAN, or generative adversarial network framework, where you pair a generator with some sort of a discriminator. So the generator here is responsible for creating eyeglasses, and the discriminator is responsible for trying to judge whether these eyeglasses are real eyeglasses from the data set collected via Google image search, or fake eyeglasses, that is, eyeglasses created by the generator. And so these two algorithms can be played off against each other in the sense that every time the generator produces a pair of eyeglasses that the discriminator thinks are fake, we can tweak the weights in the generator to make it less likely for the generator to in the future produce these fake seeming eyeglasses, and vice versa. If the generator produces eyeglasses that successfully fool the discriminator into thinking that they're real, then we again tweak the weights to maybe make it more likely for the generator to produce more of these real looking eyeglasses. Okay, so now we have an algorithm for generating eyeglasses, but there's nothing adversarial going on yet. We're just generating eyeglasses that hopefully look realistic. So the next step is to also make them adversarial. And the way we attempt to do this is by setting the discriminator aside and pairing the generator up with a face recognizer. So this is a face recognizer just like one of the ones I was talking about earlier, VGG or OpenFace. And here, this face recognizer recognizes a bunch of people, including the actors Owen Wilson and Russell Crowe, and incidentally me. And it performs this recognition with high accuracy. Now, suppose that what we want is to train the generator, teach the generator to produce eyeglasses that cause Owen Wilson to be misclassified as Russell Crowe. The way we try to do this is we cause the generator to produce a pair of eyeglasses. We affix these eyeglasses digitally, so just through digital image manipulation, onto many different images of Owen Wilson. And then we run these images through the face recognizer in order to tell whether, from the face recognizer's standpoint, any of these images make Owen Wilson even a little bit more like Russell Crowe. And we don't expect that this will work out of the box because the generator isn't trained to produce adversarial eyeglasses. But we can see whether some of the eyeglasses that the generator produces are even a tiny, tiny bit helpful towards making Owen Wilson look like Russell Crowe to the generator. And if they are, then we change the weights in the generator to make it more likely that it'll output glasses that are helpful. And if the glasses don't do anything or are unhelpful, then again, we change the weights in the generator so that they're less likely, the generator is less likely in the future to produce eyeglasses that are unhelpful or make Owen Wilson, or don't affect how Owen Wilson is recognized. And we iteratively repeat this process for a few hundred iterations until hopefully it converges. And in the end, we print out, as before, we print out the eyeglasses and we test. So this time I'll show you the result using a video. Here you see Mahmoud, who actually did a lot of this work. He's standing in front of a face recognition engine, VGG, trained to recognize 10 people in this case. You see that it recognizes him very accurately as himself, regardless of whether he's wearing his own eyeglasses or no eyeglasses, or these eyeglasses produced by a non-adversarial generator. And what you'll see next is him putting on a pair of eyeglasses that was produced after adversarially training the generator. And you see that now he starts to be pretty reliably recognized as somebody else, somebody called Ariel. And I'll give you a chance to see what Ariel looks like. As you see, this is a sort of pretty big gap in classification that's being bridged by wearing this pair of eyeglasses. Now, the whole reason we went in this direction, in this new approach, is because previously we weren't able to create eyeglasses that are inconspicuous. And you might, looking at Mahmoud, you might ask, well, did we actually now succeed? These eyeglasses that Mahmoud is wearing, they don't look all that normal either. So whether eyeglasses look conspicuous or not, this is a little bit in the eye of the beholder. Right? My definition for normal eyeglasses might be slightly different from your definition, or my definition for the eyeglasses that I'll look at twice because they are really surprising, it might be different from somebody else's. So we decided to test inconspicuousness using a user study. In particular, what we did is we created a set of, we took a subset of the eyeglasses or images of eyeglasses that we had. So some of these were, some of the images that we used were just actual eyeglasses or actual eyeglass patterns taken off of Google image search. Some of them were non-adversarial eyeglasses created by the generator, and some of them were the adversarial eyeglasses that we confirmed actually worked in attacks. And we showed all of these pairs of eyeglasses to a set of people in a user study. And for each of the pairs of eyeglasses, the people in the user study were asked to tell us whether they thought these eyeglasses were real or fake. Now, we didn't tell people that this had anything to do with face recognition or with producing eyeglasses that would fool face recognition or anything like that. We gave them a story about how we were testing a new algorithm for designing designer sunglasses, and so they were being asked to tell whether they thought these eyeglasses were real or created by this algorithm that we were testing. So here are the results. You see on the y-axis is the fraction of time that participants selected a particular pair of eyeglasses was real. So points at the top indicate that for some pair of eyeglasses, all participants thought that these pairs of eyeglasses were real. Now, since participants knew the eyeglasses could be fake, as you can imagine, they might sometimes say even for real eyeglasses that these are fake. And of course, even real eyeglasses, many of them look pretty weird. So what this bar is saying is that for the average real eyeglasses, about 60% of people, or a little bit more, thought that these were real. And there were some real eyeglasses for which everybody thought they were real, and some real eyeglasses for which most people did not think they were real. But this gives us a baseline. We want to see, compared to real eyeglasses, which is this bar, how realistic do people think are these adversarial eyeglasses? And so here's the bar for adversarial eyeglasses. It's further down than lower down in the graph than the bar for the real eyeglasses. So clearly the adversarial eyeglasses are less realistic looking. But one way to look at this is to look at the most realistic, at the 50% of real eyeglasses that look the most realistic to people. Right? So the 50% of real eyeglasses that most people thought were realistic. And you see that we see some overlap between that and the adversarial eyeglasses. So one way of reading this graph is to say that the 10% of attack eyeglasses that are the most realistic, they are as realistic or more realistic than the average real eyeglasses. So from that standpoint, we could potentially conclude that we have actually created successfully, unfortunately, an attack that fools a machine learning system, even one where the attacker doesn't have per pixel access to the input, and it fools it in such a way, in the context of face recognition, that a defender, a live human standing nearby, might not really notice the attack. Now, I haven't talked yet about camera position and lighting, so let me say a few words about that. Rather than experimentally evaluate the effect of camera position, we did so post hoc. So we used an algorithm to measure the pose of the person, or the pose of the attacker, and in particular to measure the pitch, the roll, and the yaw. So pitch is looking up and down, roll is just rolling your head like this, and yaw is looking left and right. And then we created a regression model that with pitch, roll, and yaw and input as inputs to the model, and the output is whether the attack was successful or not. And this let us explore the relationship between pose and the success rate of the attack. And we found that the pose did affect the success rate of attack. In particular, for every degree of looking left and right, the success of the attack appeared to decrease by about 6%. So if I moved 1 degree off from looking straight at you, the attack would become 1% less successful, and 6% less successful, and so on. And the effect of looking up and down was interesting. Sometimes it improved the success rate of the attack, and sometimes it decreased the success rate of the attack, depending on which face recognition algorithm we were targeting. And we were a little bit puzzled about what was going on here. And then eventually we realized, or we hypothesized, that the different face recognition engines are themselves differently robust to people looking up and down. And so it turned out to be that in the case of OpenFace, the OpenFace engine was pretty fragile to just people looking up and down independently of attacks. And so the ability of that face recognition algorithm to correctly recognize people, that ability declined faster than the success of our attack, which is why the attack seems more successful in OpenFace when people look up and down. Now, roll doing this, that made no difference in hindsight, a very expected reason, namely part of this pipeline of running a face recognition on an image is to identify where the face is, and then to normalize the face by making sure that it is upright. So basically, the pre-processing of the image undoes the roll. Now, we also we did experimentally look at the effect of lighting, and the way we did this is we put a 150-watt light bulb at a 45-degree angle from the attacker, and we varied the brightness of this light bulb from completely on to completely off in 5 different steps. And we did this as we conducted the attacks and measured how successful these attacks were. Now, we noticed there that if the attack was created without trying to account for lighting, then the attack would become only half as successful. So there'd be a 50% degradation in the success of the attack when the lighting was changed. On the other hand, we also noticed that if the training images of the attacker were collected also while varying the lighting level, then the attack again went back to working just as well as it was previously. And so if the attacker was smart enough to account for different lighting levels, then it seemed like an attacker could go back to having perfectly successful attacks again. Okay, so where does this leave us? We had only this one constraint, one set of constraints that we were still trying to see if the attack could meet, and they had to do with camera position and lighting. And it seems like the attack is at least somewhat robust, or can be somewhat robust to camera position and lighting. So now for this particular scenario, face recognition, we've checked off all the boxes. We've shown that yes, in these face recognition scenarios, where it's clear the attacker might be able to gain an advantage by fooling the machine learning algorithm, if we allow the attacker to manipulate the algorithm only in a realistic way by changing the attacker's own appearance, it seems like it is feasible for these attacks to be created in practice in such a way that they're sufficiently inconspicuous that people nearby won't notice that the attack is taking place. All right, so at least provisionally, this question of can an attacker fool a real machine learning classifier as it's deployed in practice, at least provisionally, we have one answer of yes. Now we didn't want to stop here. We didn't want to stop here because you can argue that face recognition is one particular use of machine learning. Maybe there are other uses of machine learning that are completely different. And just because something works for face recognition, maybe most other uses of machine learning and more important uses of machine learning, maybe they are perfectly robust and safe and there's nothing to worry about. And so for this reason, we wanted to take a look at another scenario that was pretty different to try to get a better sense for over the space of all possible uses, how vulnerable are machine learning algorithms. So this second scenario that we decided to look at was fooling malware detectors. So what I'm talking about here is antivirus programs, which are now pretty much standard on every computer system, on every desktop computer, laptop computer, on every server, on many mobile phones. We run software antivirus such that when we download a binary, this antivirus examines the binary and decides, is this binary malicious or is it benign? So clearly, since there are attackers who are constantly trying to produce malware, there is some incentive for them to create malware that will fool an antivirus into thinking that it's not malware. So in this particular scenario, where we're fooling malware detectors, let's again examine what are the constraints that an attack has to meet in order to be successful. Here, in terms of how the attacker can manipulate the input, the picture is very different than it was for object recognition, right? Because with object recognition, the attacker could only modify their own appearance, but here the attacker is actually the one who is producing the binary. So the attacker can change every byte or every bit of the binary in exactly the way they want. I mean, they have complete per bit control over the binary. At the same time, that doesn't mean they can change bits in arbitrary ways, right? Because if they try changing bits in arbitrary ways, then they will likely produce something that's not a valid binary and is not malicious, or at best, when it runs, it crashes. Right? So different abilities, different constraints than before. Attacker can completely manipulate the input, but the attacker's goal is to change the input only in ways such that the changed input, the changed input here is a malicious binary that it was previously detected as benign. Now the attacker wants to change it into a binary that has the same malicious functionality, but is previously the malware binary was detected as malicious. The attacker is trying to transform it into one which has the same functionality, but is detected incorrectly as benign. So here's just the attack in a different picture. We have a DNN used for malware detection. These can be trained to be effective enough, accurate enough that when they see a piece of malware, they will with high probability detect that it's malware. And what the attacker is trying to do is take this malware binary and turn it into a different malware binary which has the same functionality, but is recognized as benign. Right? And not only does this changed malware have to have the same functionality, it also, whatever transformations were performed to change the malware that's correctly detected as malware into this malware that's no longer detected as malware, these changes can't be easy to undo. Because if these changes are easy to do in a deterministic way, well, then I'll just enhance my antivirus by adding a pre-processing step where I perform this pre-processing on the malware before classifying it. So an attack can easily be undone through pre-processing isn't an effective attack. Okay, I won't talk about in great detail about how we do this, but I'll talk a little bit about the building blocks, which are techniques that were first invented for binary diversification. So the binary diversification is a process that was proposed for mitigating return-oriented programming attacks. So you probably know in return-oriented programming attacks, an attacker identifies useful sequences of instructions in a binary. These instructions are called gadgets, and then the attacker constructs whatever interesting behavior they want through pulling together these sequences of gadgets. And binary diversification was introduced as a technique where the binary would be scrambled in a privacy-preserving way, such that the attacker couldn't know ahead of time where the gadgets were, because the binary would be re-scrambled differently on different machines. Now, these techniques, a bunch of these, the specific techniques for binary diversification, we call in-place randomization, and they are these functionality-preserving transformations, like taking one instructions in the binary and substituting it with a different instruction that has the same behavior. So this is take an addition of a +1 and change it into a subtraction of a -1, and the effect should be the same. Or it can be instruction reordering, where the instructions don't depend on each other, or it could be changing around which registers are used for which operations in ways that, again, don't change the final output. And there are also some additional techniques that have to do with relocating parts of the binary. So you can imagine if you have a binary that you want to change into a different but functionally equivalent one, you could take a bunch of code from the middle of that binary, you could move it to the end and insert where that code used to be, insert a jump to this new segment, and at the end of the segment, insert a jump to the end of wherever you took out the code to begin with, and now you have a hole in the middle of the binary that you can fill in with different instructions that will never get executed, but maybe will help you in maybe will help the attacker into tricking an antivirus into thinking that this is a benign binary. So here's just a quick example of how one of these transformations works. If you have a set of instructions that you're thinking about reordering, you can do this by creating a dependency graph, which captures the relationships between the different instructions, namely when one instruction depends on another. And now you simply walk through that graph in such a way that you don't violate the dependency relationships, and you can create usually a large number of different reorderings of the same set of instructions. Okay, so that's all I'll say about the building blocks, and I'll just have one or two slides about the actual process for using these building blocks to try to create malware that evades detection. In this process, so this will be an iterative process where we have a malicious binary, which is correctly classified as malicious, and we, or the attacker, is trying to change this binary into one that has the same functionality but is incorrectly classified as benign. So what the attacker does is they iteratively do the following. They go through all the functions in the binary. For each function, they pick one of these functionality preserving transformations. They compute what the effect would be of performing this transformation on this function, and it would create a new binary with one modified function. Once they've computed what this new binary would look like, they check whether this new binary is any more likely to fool the classifier than the old binary was. In particular, it's a little bit more complicated under the covers. What we check is whether we try to estimate whether the transformed binary is moving the source binary in the direction of the gradient towards misclassification. So if it seems like this change is helpful, then we keep the change. If it's not helpful, then we revert the change and we keep going and trying with other functions and other transformations. And we essentially iterate this process for a couple of hundred iterations until it converges. So how does this work? I'll show you the results of an experiment that involved 100 malicious binaries and 3 different state-of-the-art malware detectors. Now, it's important to point out that these malware detectors actually don't have 99% accuracy, or at least they don't have 99% true positive rate. And the reason for this is that in practice, antiviruses are tuned really hard to avoid false positives. Because if you are an antivirus vendor and you have customers who think that your antivirus is preventing them from running legitimate software, then they're very likely to uninstall your antivirus. So antiviruses are tuned to avoid false positives more than they are tuned to detect all true positives. As before, we measure the success rate of the attacks as the fraction of binaries that are correctly classified as benign. So here's a snippet of results. You see the 3 different colors represent attacks on the 3 different state-of-the-art classifiers. So the taller the bar, the more successful the misclassification. Where if the bar goes all the way, the misclassification is successful 100% of the time. These bars on the left, they represent what happens when you apply these functionality-preserving transformations in an unguided way. And what this is saying is that these functionality-preserving transformations, you can apply them all you want, but if you're doing it just at random, they're going to have negligible effect on classification accuracy. So you're not going to fool the classifier by just changing the binary without some intelligent process for guiding the changes. Whereas if you look at the guided process that we experimented with, then the strongest variant of that process basically succeeds 100% of the time. So we are always successful at changing a binary that was previously classified as malicious into one that has the same functionality but is now classified as benign. Maybe more interesting or more worrisome is that this works not only against the machine learning classifiers that we installed in our own machines, but it also works against many commercial antiviruses. We tested against the antiviruses that are part of VirusTotal, and for some attacks, up to 50% of these antiviruses classified one of these transformed binaries as benign. Right? And this is despite the fact that we actually have no idea whatsoever how these different antiviruses work and whether they even use machine learning. Although an increasing number of them are advertising that they are using machine learning in some way. Okay, so where does this bring us? We were exploring this second scenario in which a second practical scenario where machine learning is deployed in the wild, and we were trying to see whether in that scenario it was machine learning. The machine learning algorithm was also attackable, and I think we demonstrated, unfortunately, that yes, it is. And an interesting property of this attack is that it's very different in terms of the constraints the attack must meet, and it's very different in terms of the attack strategy that seems like is needed to create the attacks. Now, at this point, I've gone through about 80-85% of what I wanted to talk about. I think we answered in the affirmative the question: are these attacks a threat for practical uses of machine learning? It seems like they are. Really, I shouldn't draw a green checkbox because that seems like a positive thing, but this does not seem like a positive finding. So now I want to switch to talking a little bit about defenses, because there's been tons of work on defenses. One of the major categories of defenses has to do with explainable AI, trying to explain why a particular algorithm made a particular decision on a given input. And this is actually a good fit for some contexts, in particular contexts where the defender is manually examining the input. So if you think back to the face recognition scenario, if somebody is looking at a video monitor that's showing people passing through a checkpoint, and this video monitor is able to highlight the fact that the recognition of a person is based completely on the eyeglasses, well, that might be enough of a signal to the police officer to be able to tell that something bad is happening. And in fact, So one of my colleagues, Matt Fredrickson, is putting a lot of work into these explanation techniques. So some of his explanation techniques can show here on the left side, one of the students involved in the project. The bottom two images, she is not wearing attack eyeglasses. In the top image, she's wearing attack eyeglasses. And now in each column, you see which parts of the image are important for which for the different layers in the network as we go closer and closer to the output. And we see that for a set of layers in the network, it seems like the eyeglasses are becoming the dominant factor for the classification decision. So if a police officer was shown this as somebody is passing through a checkpoint, that might be enough information for the police officer to be able to tell, oh, look, this seems like it's an attack. There are other directions for defenses. Adversarial training and provably robust training there's been a lot of work on both of these. Adversarial training trains an algorithm with both benign images and attack images, but unfortunately needs a large collection of adversarial examples to work well and doesn't give any guarantees. Provably robust training in principle gives you a strong guarantee even if you don't know what attack you're going to see later, but doesn't scale to large networks, potentially degrades the accuracy a lot, and it only focuses on attacks where the inputs are changed a tiny little bit. So really these attacks like we were talking about with the eyeglasses, which change many pixels of the image, even though the human still thinks this is the same kind of image, or change the binary dramatically, those attacks are out of scope. Another thing that's interesting to consider is whether attacks can be used as defenses. So certainly already I've mentioned adversarial training. The better the attacks we can generate, the faster we can generate them, the better we can train algorithms on these attacks to be resistant to similar attacks. It turns out that this also has some additional beneficial properties, even attacks aside. And you can also imagine using these attacks against bad uses of AI. So my colleagues Carmela Troncoso and Sera Gurses and their students and postdocs, they've been talking about something they call protective optimization technologies, where you might use attacks like this against harmful uses of AI. So maybe face recognition for mass surveillance, or when companies used algorithms for making hiring decisions automatically but in a biased way, or insurance coverage decisions also automatically but in a biased way. You can imagine trying to attack those things, and that would be societally beneficial, perhaps. Of course, it's not so clear how well this can work, because to evade mass surveillance, and my attack on mass surveillance might work 100%, might have to work 100% of the time. If it fails even sometimes, I'll still be detected as me, and maybe a lot of these attacks require more resources or more knowledge than most individuals will have. So at best here, the glass is half full. There's some hope for defenses or for using the attacks in a beneficial way, but it's not clear that this is likely to work super well or outweigh the harms. Now, the last thing I want to touch on is, why should we as cybersecurity experts care about all this? One reason, which is sort of by definition, is that, well, cybersecurity is about the security of algorithms. Machine learning algorithms are algorithms, so we need to care. But also because cybersecurity really needs machine learning and AI, and so we should care about the ways in which we use machine learning and AI can be attacked. Why do we need AI and machine learning and cybersecurity? Well, I think we know we're falling behind. The attackers are increasingly sophisticated. We have more and more systems to defend. The attackers can use AI and machine learning against us to create better attacks. So really, we need to bring something more to the table. And it turns out that there's a lot of research and a lot of promise in using machine learning and AI for defense. So just to give a few examples, in terms of application level or fixing software, there are tools to automatically detect vulnerabilities in source code binaries. There are even tools and algorithms and approaches where you use machine learning to automatically repair binaries. So not just detect bugs, but detect how the bugs should be fixed. We have tools that at the network level And so I'm sort of being too optimistic when I say tools. We have ideas about how to build tools that will allow us to automatically reconfigure networks to defend against attacks at scale. So we've had software-defined networking for a while, but often the way we use software-defined networking is one network admin calls up another network admin on the phone and tell them, oh, we're seeing these kinds of attacks. Let's reconfigure our network in this particular way. But you can imagine this being done in a much more automated fashion. And there are demonstrations or sort of specific examples of how this can be very effectively done in an automated fashion to, for example, defend against distributed denial of service attacks. Another potentially wonderful use of machine learning at this level is to generate data that would be difficult to share. So you can imagine situations where it would be really useful to share between different companies data about attacks on their network, but that data might be hard to share if there's a lot of private traffic. So if you can instead construct a model of that traffic that produces similar data but not the specific data from a network, then that might be okay to share. At the human level, there's also a lot we can do. So we can now with our algorithms to predict which systems or which users are going to be compromised soon, so that we can take action before that actually happens. There are algorithms for, and we need better algorithms for detecting misinformation in the news media, and we can think a lot about algorithms that will help users make better decisions when they're going online, deciding whether to share a piece of private information with a particular website, for example. But many use cases like this. Okay, so to wrap up, I wanted to do three things. I want to show that for real world applications of machine learning, it seems like attacks are possible. I showed this for face recognition and for malware recognition. I discussed defenses a little bit. They have a long way to go. There's a lot of work that needs to be done there. And I hope I highlighted that there are many opportunities in cybersecurity for machine learning to help. And in fact, many of these uses of machine learning in security, maybe we need to worry about attackers going after the defenses that we build, but maybe in some of these situations, actually the attacker doesn't have enough access to mount successful attacks. And with that, I'm done, and I'll be glad to take any questions.
Thank you, Lujo, for a very interesting and stimulating talk. As a matter of fact, we had quite a number of questions on the Slack channel, so we won't have the time to go through them all, but just taking a few of them, starting with the question by Riccardo Lazzaretti. So he's asking, once we have created eyeglasses that confuse the model, changing Mahmoud in Ariel, what is their behavior with other subjects? If I wear the same eyeglasses, I'm identified as Ariel, me, or someone else?
Yeah, great question. So the specific attack I talked about changes a specific attacker into a specific target. We also experimented a little bit with, can we make generic eyeglasses? So can we make one pair of eyeglasses that will change many people into a particular target, or many people to be not recognized as themselves? And this works to some degree. So we have various experiments which show if we produce 10 different pairs of eyeglasses, we can get to that to, I don't know, something like 90% of the population will be incorrectly recognized, not necessarily as a specific individual, but as somebody other than themselves. At the same time, these eyeglasses then become a little bit more strange looking, so they become a little bit more conspicuous.
Yeah, thank you. Another question by Fabio Rolli. So what about the transferability of this attack against an unknown face recombination system?
Yeah, that's a great question. We didn't try to do anything to increase transferability, but we experimented with transferability a little bit, and we found that some of the attacks do transfer. So I don't remember, between VGG and OpenFace, I think the attacks transferred about 2/3 of the time in one direction, but not so well in the other direction. So it certainly seems like transferability is a property that these attacks have.
Okay, that's very interesting. The last question by Luca Demetrio is on the malware, the work he did on malware. So how much the adversarial malware grows in size using this rewriting technique? And these, what are the performance under packing and obfuscation, in particular for finding functions inside the binary?
Great question. So we made it easy for us, and we did this. We were performing all these experiments on unpacked binaries. So which is only, of course, is only part of the picture, but it is an important part of the picture. The different attacks have different effects on binary size. So there's some attacks that don't affect binary size, and those are a little bit less effective, but still pretty effective. And then the attacks that we were experimenting with that were the most effective, they would increase the size of binaries by up to 5%. So basically, up to 5% of the binary could be taken out, move to the end, leaving some space for different sequences of instructions whose only purpose would be to help in evading the malware classifier.
Okay. Thank you very much, Lujo. So the time, we are running out of time. So the next sessions are starting in a minute. So it was really a great pleasure to have you here. So there are still a few questions pending in the Slack channel. So I will ask you, Lujo, to join the channel. So perhaps you may want to give a look to the questions and perhaps reply to them. So that would be great if you could.
It would be my pleasure. Thanks very much.
Thank you. Thank you very much, Lujo. See you soon.